as you remember, in our previous study, we investigated the ground state of the conjugated polymer, specifically PD/PP conjugated polymers. So totally, my major focus in my doctoral dissertation is force field molecular dynamic of these polymer systems. And for some part of that force field calculation, we found that there is a lot of room to investigate the influence of the some acceptor units, for instance, PCBM or density or ITIC acceptor unit on the, for instance, aggregation or some other morphological properties of these conjugated polymers. So also that was in a good conjunction with Dr. Killin's suggestion about investigating the electronic structure of the PD/PP conjugated polymer as a blend with the PCBM and also with a newer acceptor unit, ITIC. So, Dr. Killing, can we go forward? Yeah, totally. As you know, semiconductor materials have attracted a lot of attention in the solar cell industry. Actually, mostly this semiconductor material that is using in this industry is silicon, because it shows higher power efficiency. But recently, people are interested in newer, maybe less expensive, more flexible conjugated polymer materials. Dr. Killian, if you go next. So totally, to date, the silicons show best power conversion efficiency up to 20%. For sure, they are best materials right now, if you just want to consider power conversion efficiency. But conjugated polymer, comparing to this, actually organic polymers or conjugated polymers, comparing to the silicon, they are more flexible. They have tunable mechanical properties. For instance, you can easily use sidechain engineering to tune the mechanical properties to the desired or to target variable, for instance, to reach some flexible or bendable materials. But the power conversion efficiency of this conjugated polymer is not such that high yet. Actually, the research on this area is in its infancy, maybe with newer acceptor units, maybe just around 10 years, researchers are working on this area. So several reported value for power conversion efficiencies are observed, usually from, for instance, 4 to 11% for these semiconductor materials. There is some messages. Should I read them, or we can do that?
Yeah, you can read. And before, is it right that right panel should tell polymers, organic polymer solar cell? Now it shows silicon and silicon.
Sorry, the right one you mean? Sorry, yeah, that was a typo. The right one is organic semiconducting polymer. Yeah, sorry for the typo. Dr. Han asked, what's PCM and ITC? PCM is, we have in the next slide, Dr. Killian, if you go next. It's
it's not next. Let's discuss it by word or promise to address it later.
Actually, PCBM is a functionalized fluorine, compare of C60 carbon buckyball, and it's most used actually acceptor unit for this conjugated polymer, but it has some good properties, for instance, charge transfer or solubility with the chlorobenzene. Also have some problem, for instance, weak absorption properties. And ITIC, I didn't see any reason why the name is ITIC. All the literature just mentioned is ITIC, but the chemical structure is similar to the, for instance, a monomer of conjugated polymer, for instance, PDBP. But the difference with other acceptor is that they add some alkyl side group in this actually acceptor unit to tune its mechanical property for some morphological purposes. For instance, if they increase or decrease the chain lengths of those side groups, they can help the conjugated polymer, for instance, with better pi stacking and having better overlap in the orbitals of those polymers to improve the interchain charge transfer. However, we did not do a lot of calculation yet on this polymer system. We already submitted jobs, but not that much. So, Dr. Kilin.
And what is blend? It's another question of you.
Yeah. When we are talking about the blend, we are talking about, for instance, for our DFT computational model, we have a dimer of DPP conjugated polymer, and we put 1 unit PCBM acceptor in the periodic cell. But in the bulk system, for sure, we have a different fraction for those materials. For instance, addition of PCBM into a pure DPP conjugated polymer system. So when we are talking about blend, we are talking about having both in the simulation model.
And let me add to this discussion of definition. So in more standard solid state photovoltaics and in novel perovskite photovoltaics, there are well-defined layers. And actually in previous slide where Amir is offering N-type and P-type semiconductors. So there are different materials. And in polymer plastic photovoltaics, there is an interesting approach that the question of Yvonne is very deep. It was throwing me off for several years. I never studied it systematically and was sitting on talks and I was not understanding where is donor, where is acceptor. So one makes a mixture of molecules that serve as donor and as acceptor. And there is a belief that since they are in amorphous, approximate alternating order, so there are 2 lattices. One lattice of donors, one of acceptors. And since their electronic structure, their gaps and bands do not coincide, electron hops from one electron acceptor to another, just skipping the hole acceptors, and hole jumps from one hole acceptor to another. So it is like 2 materials blended together. And for computation, it is interesting challenge to look for elementary charge separation between one donor molecule and one acceptor molecule. But for more global scale engineering or for multi-scale material modeling behind atomistic, one considers interaction of these sublattices and simultaneous travel of charges further to contact. Okay, and I know it is a trap, but Amir, please consider to discuss these subjects, and I'll assist as needed.
Sure. So discussion of CT, you mean charge transfer, transport, if I'm not wrong. So why charge transfer happens? So usually when we have 2 molecules, one donor and one acceptor, and over, for instance, photoexcitation, usually we expect that 1 electron from HOMO in the acceptor unit, in the donor unit should be excited to the LUMO of that the donor unit, and then followed and transferred to the LUMO of the acceptor unit. So usually this transfer between HOMO and LUMO of donor and acceptor should cause the charge transfer over photoexcitation for this DA or donor acceptor units. Dr. Kinney, I need your help a lot for these slides, I think. So if I'm...
by now you're telling better than I can say. Everything is reasonable.
Thank you. So Which electron properties of donor and acceptor facilitate charge transfer? So to me, it seems that I don't know, the energy level of the HOMO and LUMO in those systems is important for sure. But can you clarify us, Dr. Killian, help with this? And also Dr. Han and Aaron are welcome to share their opinion.
So, Amir, I think you told everything in the previous statement about explanation why charge transfer happens. So, in nature of objects, all systems try to go from higher energy to lower energy, right? And if we focus only on conduction band, only on unoccupied orbitals, if you have photo excited LUMO of donor and LUMO of acceptor is a little bit lower in energy, then it will be natural to go down in energy. Just it's more thermodynamically, more statistically favorable. So it will go towards lowest energy, even if you do not know the mechanism.
Okay, and why electron jumps from one orbital to another? You already answered that question, I think.
No.
You didn't?
I didn't. And feel free to ask opinion of Aaron and Yvonne.
Yeah, for sure. Any discussion is much appreciated.
Like if you have two molecules, one is photoexcited, another is not, and thermodynamically the electron should jump from one to another. But ideally, all good quantum mechanical orbitals are orthogonal. So why electron should jump from one orbital to another, from one molecule to another?
So at this time, I do not have a certain answer for that. So I need help. Maybe Aaron, Dr. Han.
Yeah, I think Aaron has some verbal formula to share.
I guess if you just consider that if you have, I don't know, like a charge in a box, in this case, the box is a molecule, like it can just interact with like the molecular vibrations of the molecule. So the electron can jump from different spatial regions by interacting with the lattice vibrations.
Yep.
And the main like thing that we compute that describes that is the non-adiabatic coupling.
Okay. And how does it relate to orthogonality of orbitals?
So it helps, I guess, break the orthogonality in a sense.
Yep, I'm very happy. It's my favorite statement. Thank you, Aaron. Amir, does it? Do you agree with everything Aaron told, or you need more details?
For sure, I need more study on that, but I appreciate Aaron's answer. Yeah, that was fine. So this is why maybe also Aaron already answered the next question: the role of molecular dynamics for some non-adiabatic coupling, or considering some real situation, especially for this study, either for blend or pure polymer, for instance, investigating the influence of the temperature, changing temperature on the some electronic properties of the systems. So
yeah, all correct. So if there is no molecular motion, if all geometries are optimized, then electronic orbitals are orthogonal means that their transitions between orbitals are for sure forbidden. And we need to violate this orthogonality by something, by shaping system and slightly changing the shapes of orbitals. The higher the temperature, the more molecular vibrations, the more chance for such transition. And the rest of the other technical details are how to quantify this connection, how to quantify connection between vibration of ions in the molecule and probability of electron to jump from one to another orbital.
Okay, thank you. You go next.
Yes. So there are three slides of traps. This is the second one. So Amir, would you please comment your vision, and Aaron and Yuna are very welcome to criticize if something is wrong here.
So we have Dr. Killen donor and acceptor unit, for instance, in the left. As you mentioned, over photoexcitation, we expect if we consider the first column in the left, electrons should be excited and go to the LUMO, for instance, LUMO D. And then because the LUMO of the acceptor unit, as you mentioned, Dr. Killen, has the lower level of the energy, usually it is expected to have a transfer from LUMO D to LUMO A, from donor to the acceptor unit, because of you mentioned, in the nature, it's common that system tends to go to the lower energy. And for HOMO and LUMO of acceptor unit is expected to have lower energy for sure. So, and for the hybrid system, I need your help again, Dr. Killen. So if you can put some comments on that.
Okay. So there is a thank you, Amir. You told everything correct. There is a little discomfort in interpreting and speaking about these systems in the following. There is a discomfort with nomenclature. If we make a single run in single simulation cell of a single molecule, we have well-defined HOMO and LUMO orbitals, and they have specific numbers, right?
Yep.
If you take another molecule, it's also well-defined HOMO and LUMO, and they have well-defined numbers, and we can call them LUMO of HOMO and LUMO of donor, HOMO and LUMO of acceptor. But if we bring both donor and acceptor into one simulation cell, how the orbitals in this hybrid system relate to the orbitals of the individual components?
Sorry, can you repeat your question again?
If we place two molecules into one simulation cell,
okay,
how the orbitals of the combined hybrid system relate to individual orbitals of the isolated molecules?
So in the hybrid, for instance, if we have acceptor and donor unit, we expect to have for instance, LUMO in the acceptor unit and HOMO in the donor unit. But about the level of the energy for those orbitals,
I'm just going to edit mode. Yeah, please keep talking. I want to edit.
I'm not exactly sure, Dr. Killen. So, for instance, for the HOMO of the acceptor and donor unit, we expect that in the acceptor unit we should have a lower energy level for that. But for the hybrid function, I don't know, it could be just a algebraic summation of those energy levels, or
approximately. Of course, there will be some interactions that change energies, but very approximately, especially if there is no chemical bonds between donor and acceptor, orbitals act just as a simple addition. So if one takes energy of donor HOMO in the mix, you can do a little arrow, and it will be approximately at the same energy. And here it is symbolized by blue color. If you take energy of the energy of donor LUMO, so here are blue dashes, it will be up, it is expected to be at the same energy, and here it is symbolized by blue color. Now if you look for acceptor, so energy of acceptor HOMO is expected to be at the same energy, and therefore it will be not the it will be somewhere inside the valence band. So it will be not the a frontier orbital anymore. So HOMO of hybrid will be primarily composed of the HOMO of donor only. And in this diagram, we consider specific arrangements of two molecules which are already served as donor and acceptor. If one mixes other molecules, relative order can be different. And LUMO of acceptor also keeps its energy, and it expected to happen to be the lowest
I see.
lowest energy in the hybrid molecule. So if we start practical calculations, we expect that lowest orbital in the conduction band of hybrid will almost coincide with lowest orbital in the acceptor. And the highest orbital in the hybrid will approximately coincide with highest orbital of donor.
Okay, yeah, we can plot those and present them later also to see how these energy levels looks like in the real situation.
Also, in very rough estimations, not for high precision, the energy difference between energy of LUMO of acceptor and energy of HOMO of donor approximately give the open circuit voltage for the solar cell composed of these components. So if you need to publish in some practical applied forum and you do not have time to do some advanced calculations, you can just compute these two basic things and tell my calculations predict what will be open current voltage for this solar cell. And there is a chance that your prediction will be quite close to experiment.
Okay, very good.
Amir, do you have any comments on
the hybrid system? Yeah, you already explained that. Thank you.
Okay. And now we return back to your original slide.
Okay, this is the PCBM blend that we used just once as acceptor unit in conjunction with the dimer of the DPP polymer system. Yeah, I have one practical question about DFT calculation, Dr. Kilin. So in the, for instance, molecular dynamic or in the real synthesis, we have different fraction of PCBM comparing to the polymer system. Okay, for instance, 10% PCBM versus 90% polymer, for instance. I'm not sure about the exact value. So here we have just a dimer and a PCBM unit. So
So
does
it's about relative concentration.
Yeah. For instance, do we need to increase the size of the polymer model, for instance, going from 2 monomer to 4 or 5, or no? It should.
Even if we need, we shouldn't do it because it will be very expensive. The number of atoms is quite cheap in Rust, but volume is quite expensive. So if you want to do bigger systems, first one needs to make an effort in squeezing and bringing system to realistic density, to have no vacuum, to do dense packing, which would be much more efficient using your primary professional skill from Professor Shah group. So take the model, apply pressure, and keep compressing until it builds up to the realistic density. Right now, it's very fluffy. It has a lot of vacuum between.
Yeah, I see. Okay, thank you. And yeah, this is the most maybe traditional acceptor unit used for this polymer system. There is several advantages, for instance, high electron mobility or solubility with chlorobenzene, which make it an attractive option for an acceptor unit in conjugated polymers. However, it has several problems that, for instance, it may cause some aggregation, exaggerated aggregation actually in the bulk system. Also, it has a very weak absorption spectrum. So because of this, in addition to the PCBM, we are trying to test some other acceptor units. For instance, the most popular one that recently researchers are working on is ITIC. We started the modeling of that system. We submitted some jobs, and we hope to have two acceptor units, and then choose one of them as or at least to provide some qualitative study between this two acceptor unit in some fundamental level, for instance, level of atoms and electrons. Dr. Kinner, could you go next?
And I think it relates now with the structure. We can fully answer on the question of Yulun. So P stands for this phenyl ring. C stands for this
Archibald.
C carbon, so many carbons like C61, and butyric stands for this B for this alkyl chain of certain lengths, and then methyl ester for this group, something like that. This was a little discovery transferring buckyballs from fundamental science to the applied science, because buckyball without this group is not processable. It's one can only, I don't know, deposit in vacuum or for short time sonicate it, but it deposits into the sediment very quickly. And with this group, one can put it in solution and do paint or whatever processing chemical.
Thank you, Dr. Killen. So this is the computational model from different perspectives. So the system, again, we use the system that we had in previous paper, a 2 monomer, actually a dimer of DPP conjugated polymer with C68 side groups, and also one acceptor unit. PCBM is located and the system is optimized at the ground state, and also is running for some molecular dynamic calculation. So the most available results are provided in the following slides: the orbitals and absorption spectrum and the DOS of this blend system. So when we are talking about the blend, we mean this computational model actually, a dimer of DPP polymer and PCBM acceptor unit.
Okay.
Next.
Amir, let me give a quick comment. So for future research steps, practical computations of charge transfer will be much more comfortable if you rotate this model by 90 degrees around y-axis. It sounds a little silly, but we do have a set of codes which are pre-made and they optimized to explore charge transfer in direction along z-axis. So here your donor and acceptor are displaced in space along red axis, along x-axis.
Actually, the backbone right now is along the y-axis. So
yeah. So if you rotate around y will not change. If you rotate 90 degrees around y, it will swap x and y axis.
Okay.
So in the procedure rotate underscore xyz, you just launch it and then set 0, 90, 0, and then it will rotate between around y, which means it will swap x and z.
So what's the desired state? I didn't get that. You should you want to have a polymer backbone in the z direction or y direction?
No. Keeping polymer backbone in y direction is good. But right now, if you look on the upper right,
okay,
the polymer and buckyball are offset from each other along x direction, right?
Okay.
So centers of polymers and center of buckyball are shifted comparing to each other along x. They have different x coordinates.
Okay.
And we do have set of working codes that optimized for donor and acceptor being shifted along z direction.
So usually the location of the acceptor unit shouldn't be based on the optimization, or no?
What I suggest is not redo the model, not re-optimizing model. If we just rotate it complete axis and keep the same size of the cell, the geometry will stay optimized.
Okay.
It will only redefine the axis. And rotating a model will be a little quicker than rewriting the codes.
Yeah, and so what's the reason? It's for some post-processing codes that you have?
Yes.
Okay, sure.
And I apologize I didn't bring it up earlier, but still it's better to catch it as early as possible before too much results are created.
Okay, sure. So before doing, for instance, MD calculation, we need to rotate that.
Ideally, yes. If you already if you have done a lot without it, you can find shortcuts. But at least for orbitals, for ground state orbitals, one needs to do this rotation.
Okay, sure. Okay. How to choose? Dr. Han asked question. How to choose a reasonable initial configuration? Does relative position of C60 and polymer matter? Very good question. That was also my question. Usually we do some force field optimization, but yeah, I have this question from you, Dr. Kirin, because you add this blend. So if we, for instance, rotate that PCBM 180.
No, we rotate the whole cell.
No. I'm talking about Dr. Han question. For instance, we put the PCBM in this position. What if we move it several angstrom in the y-axis direction and then optimize the system? What should we expect from that movement?
Results will change. I do not know how strongly, but for realistic results, one may either explore different mutual positions and then average over them, or make a big cell that contains multiple buckyballs and multiple polymer strands, and so that they explore all possible or majority of possible positions. Yes, it is a serious question that could be hard to address in the first place. So maybe making a little representative example of only one mutual position is quicker to complete, with understanding that it misses some details. What seems to be most important is a relative position of the this carboxylic group from the PCBM and the active groups in the backbone of the polymer. So depending of whether we directed oxygen towards polymer or oxygen outside of polymer or 90 degrees, this may create some changes. But the correct but maybe unreachable answer to Yu's question is to slightly increase number of threads in PCBMs, slightly, so that it still will be calculatable, and processes this force field by compressing to a realistic density. When they're compressed together, then they will experience much more realistic configuration of interface. In this interface, the molecules are separated by vacuum. Even if one takes into account the dispersion forces, it may not optimize naturally to come to closest distance. And when one compresses, they are smashed into each other just mechanically. And this shortens the distance for electron to travel. This increases orbital overlap, and it increases the rate of charge transfer. So making compressed dense packed model is natural step in this research.
So if reviewer asks you, okay, we know this difficulty, so what was the reason that you put in this position? Is there any logic behind that, or
one just optimizes and allows system to find the position it likes?
But even move the system, we should expect a drastic change in the results, or no? Some.
If the answer would be known, then there will be no reason for calculation.
Yeah, you're right.
But just the most correct approach is to compress, and then it will remove potential questions of the reviewer. If it is not possible, then one can do a first shot as is and promise in the conclusions that the next step is to compress.
Okay, thank you, Dr. Killian. So these results in coming slides are shown as you see the orbitals. Actually, the previous one was for the orbital 469, that was HUMO, and for this orbital 470 for the LUMO, we can see that actually this is the orbitals from different view. Okay, they are the same. We can see that the LUMO is actually composed around the acceptor unit. However, in the previous slide, we saw that the HUMO is distributed along the backbone of the polymer, or actually the donor. So we have HUMO on donor and the LUMO on the acceptor unit, something related to the discussion that Dr. Killian mentioned about the level of the energy for those systems. And do you have any comment on this, Dr. Killian? So it's not surprising that for every acceptor unit, always LUMO should be observed on the LUMO, right? If I'm not wrong.
It is very expected, and it is encouraging result. So based on this arrangement of HOMO and LUMO, it enables to continue this project and makes it promising to continue. But if you plan to do next steps, maybe one may want to show few more orbitals above and below. Especially one needs to find which of the LUMO plus something, plus 1, plus 2, or plus 3 will be again on the donor. Because we need to simulate first how the electron is promoted from occupied to unoccupied on the donor, and then subsequently how it transfers from donor to acceptor.
Okay, very interesting. And could you come back? It's related to Dr. Han's question. Is there H on O atoms for donor or polymer system, for donor or acceptor unit, Dr. Han? Or it doesn't matter for both? Yeah, the systems are neutral here. So that was your question, that system is neutral on the, on the O atom in the, no, it's actually double bonded to the carbon. So we do not have any oxygen on the O. If you are talking about the polymer system, if you come back, Dr. Killen, to previous slide. No, the next, please. Yeah, for the left side, you can see the oxygen is connected to the carbon or to the pyro ring with the double bond type. So no, we do not have any hydrogen on that. That was your question? Okay. Could we go next, Dr. Killen?
Yeah, there is another little trap. So data on the right are from Emil, and little hand scratch on the left is from myself. So the left shows ideal expectations, right shows true calculations. So Emil, please go ahead and tell the story.
Thank you, Dr. Killen, for rearrangement and some beautiful paintings.
I doubt the bed.
For the DPP polymer system, the bottom right, that was from our previous studies, pure polymer system, band gap was observed around 0.9 electron volt. However, after adding the acceptor unit to the system, it decreases the band gap to 0.55 electron volt. Unfortunately, I do not have the results for the PCBM alone to see how its DOS looks like, and to do also some comparison between the level of the HOMO and LUMO for the PCBM, for the pure polymer, and for the hybrid system, actually the blend, as Dr. Killen commented in the earlier slides. So, but here we expect that maybe, as Dr. Killen mentioned, if we compare the energy level of HOMO and LUMO, yeah, HOMO should be from the donor unit at the end, and LUMO is the acceptor unit in the final density of a state. I will try to provide some results in coming meetings to further see that this system is following that logic or not. So, Dr. Killen, could you please add any more comment on this part?
No, you explained it nicely.
Okay, thank you. And could we go next? Yeah, here again, we do not have the results of PCBM yet. So for the blend system and for DPP polymer system, we can see that the blend system, the results are actually of the absorption spectrum are a little shifted to the right. So I'm not sure about this result to see that, yeah, this blend has a stronger absorption. Could we say this difference, for instance, 100 nanometer and big improvement in absorption or no. But totally, this PCBM system, one of its weaknesses is weak absorption. So I expect, for instance, if we replace the PCBM with ITIC polymer system, we may have a better improvement in the absorption, or actually the location of the peak. And yeah, we need more results on this. So Dr. Killian, if you have any more comments or suggestions on that, I would be grateful.
In 3 slides from now, you are showing experimental results for PCBM absorption. And it looks like PCBM itself has the edge of visible and UV. So in about this region. So
exactly, yeah.
This peak may correspond, well, maybe either this or something that is not shown in this region. Some features at the border of UV and visible may come from PCBM. Here, it looks like it's just a little shift of the transition energy of the polymer peak, because the charge transfer transition from buckyball to the polymer should be dark. So it could be located in the infrared region, but give negligible contribution to absorption. So it looks okay. No big surprises. Would be interesting to add a line for PCBM whenever it is available.
So totally, from the gamma point only calculation, could we have a? I'm not sure. Maybe it's a silly question. For instance, if we do key point sampling for both systems, should we have better comparison or better results, or no? Even for a single point calculation, we should have the general trend in the system.
Thank you for the question. The PCBM itself will not change with or without K points because it is isolated mode. It doesn't have PVDs.
Yes.
The contribution from polymer will change. But if we are not thinking of quantitative predictions to guide experiment, but if we focusing only on main trends, then gamma point is a reasonable approximation on one hand. On another hand, if we are cynically considering how to pass through screen by reviewers, then you'll be able to refer to your previous paper where you already consider the consequences of including multiple K points, and you can say by words instead of adding results that in presence of multiple K points, the lowest energy band will be broader and more intense, but qualitatively it will be still above the level corresponding to charge transfer from to PCBM.
Okay, thank you.
It's okay to do it, but your time is also a precious resource, and if there are ways to explain something by words rather than computing, why not?
Yeah, I got your point. Thank you. As we discussed, there is some, although this is most common acceptor unit these days for this polymer system, but there is some drawback. For instance, difficult to tune energy level of the system for visible light absorption. We can see that in the coming slides. They tend to aggregate or form aggregation region in the bulk system. Sometimes it interrupt the flexibility of the system, which is not desired for some, for instance, flexible or wearing polymer system. And usually non-fluorine acceptors with some, as I mentioned, with some flexibility in tuning the mechanical properties are more desired. So as it is reported in some literature, so for instance, the ITIC based polymer solar cells show power conversion efficiency up to 6%. However, with some specific papers, I saw that they reported the value of this efficiency up to 12%. So it seems that they are doing better jobs than PCBM, and in the near future, they might be completely replaced by ITIC, actually having ITIC instead of the PCBM. So could we go next, Dr. Clint? Yeah, this is the system, or actually the acceptor unit of ITIC. As you can see, so there is a specific components here, but as you can see, there is in each side two C6A13 alkyl group that are very interesting for tuning the actually mechanics and prevent the aggregation of the system that is closely related to pi stacking and also interchain charge transport of the system. So because of this, maybe these polymer systems are getting more popular in material science community comparing to the traditional PCBM acceptor. Could we go next, Dr. Killen? And yeah, in the case of the absorption spectrum, we can see that for PCBM, it has a big absorption capability. However, for the ITIC, as you can see in the left, the absorption spectrum, it's much higher. For instance, it's very close to the absorption of the P3HT conjugated polymer, which is a commonly used conjugated polymer model. So it not only has the bad and doesn't have any bad effect on the absorption, but also may help the system to have a better or a stronger absorption. We are trying to see if it is true or not. So we will see the results in the coming weeks about that.
May I ask a question, maybe not to Amir, but to Aaron? So what, and I do not know the certified answer, only hypothetical. So what is the reason to select acceptors with high absorption if our original idea that the donor is accepting a photon and then transfers an electron to acceptor? So in this original diagram, original scenario, the absorption of acceptor is not involved. So we have donor and acceptor plus photon gives excited donor neutral acceptor, and then there is a donor becomes positive and acceptor becomes negative. So in this scenario, absorption of donor doesn't matter. So Aaron, would you try to bring in an idea in which scenario absorption of acceptor is important?
I guess if you're donating the opposite charge, then you just flip all the arrows around. So instead of an electron, I guess it's hard because you just have to change all the terminology. So in this case, it's an electron acceptor. But if it was a hole acceptor, you would just swap the all the arrows and all the orders of the names, and you get the same process.
Yes. So if this is not most elegant if we call donor and acceptor related to electron, but if we photo excite acceptor and then the hole is in the valence band is jumping from what we originally called acceptor to what we originally called donor, right? Are we speaking about the same thing?
You mean you're talking to me?
Yes.
Yeah.
Okay. Yeah. Thank you, Aaron. Amir, does it make sense to you?
Yes, and very interesting to follow more. I'm a little. I need to study more, to be honest, to have more vision about or more insight into the
So
those concepts. But yeah, very interesting point to.
in the traditional consideration, we promote the excite donor and then electron jumps from donor to acceptor.
Yes.
And in this non-traditional, which you just brought up by mentioning that this new acceptor has higher absorption, we may consider optical excitation of of this ITIC, and then the hole, like absence of electron in the valence band, will jump in space to the polymer. So two channels instead of one can realize in this material. So there are two pathways to create the same electronic configuration to promote charge from polymer, to create charge transfer between polymer and this ITIC acceptor.
So you mean at different energy level, polymer and also the acceptor unit may change the role? For instance,
no. The direction of charge transfer will be always the same, but it would be involving different orbitals. In traditional path, the electron negative charge will be moving from PDPP to ITIC, from donor to acceptor, and in the non-traditional, the hole, which is absent of electron, will be moving from ITIC to PDPP.
Okay, I see.
So it will involve different pairs of orbitals. In the first channel, it will involve LUMOS, and in the second channel, it will involve HOMOS.
So I have a question. For instance, for the DPP PCBM blend, I saw that I just checked frontier orbitals. For instance, 3 LUMO orbitals, 3 occupied orbitals, for instance, near the gap, and 3 unoccupied orbitals. I saw that, for instance, HOMOs were on the actually the polymer system, and all LUMO or unoccupied orbitals were on the acceptor unit.
But you can keep looking further, like 5 or 10 above LUMO and below HOMO, and finally you'll see orbitals of on LUMOS will be alternating, one on donor and another on acceptors, and occupied will also be alternating. One on donor and another on acceptor. And if you keep scrolling to really highly excited orbitals, they will start hybridize between donor and acceptor.
Okay, I see. Okay, thank you, Dr. Kulin.
Okay. Ready for your next slide?
Yes, there is. I just have some few asides. This is the ITIC system that I model to do some excited state calculation. For sure, we don't need to be worried about the periodic system. Just maybe isolated acceptor unit here. So it should be isolated, Dr. Killian, right? Because I think that it is in the bulk system they are putting such that molecule as a acceptor without repeating that.
Yes, it is a standalone molecule without periodicity.
Okay. And also the other system that is running is the blend of the DPP with the actually as a blend with ITIC. And yeah, the system is running, and these are just some simulation models. So you mentioned to decrease the size in the Z direction, Dr. Killian?
Two things. Please consider to rotate around Y direction.
Oh, as you mentioned before, yeah.
So right now your Y is this green.
Yeah, the Y is the same because we know the.
Oh, this periodic.
Exactly,
right.
Yeah.
But if you rotate by 90 degrees around Y.
Okay.
So it will swap the X and Z. So right now it looks like you show the donor and acceptor, they are stacked in the plane of the figure, right? They are in front of each other.
I checked them in Material Studio before having there. I did my best not having any stacking in the system. So
well, they are set in space, but right now it is hard for us to see because the acceptor is arranged a little bit closer to us, and donor is moved to the back wall of this.
Yeah, I see. Also, it has some side groups, and also it's very large molecules. It's not
yeah,
smaller than the.
If they entangle with side groups, it is okay. It's not a problem.
I will take a look for sure. It's not a big deal to rotating the.
Yeah, and if you perform this rotation, then it will be like acceptor will be on the bottom, and donor will be on the top, in along the direction. So right now you have donor to the bottom, acceptor to the front, along X. And if you do rotation along Z, they will be offset in space along Z direction.
Okay, I see. For sure, I will rotate them.
And there is a question in the chat line.
Like the 100 DPP polymer is bound to the ITC. How? I don't know what's the meaning of bound here.
Chemical bound.
Oh no, no, they are not connected to each other. Just some cohesive energy between those molecules. But yeah, we have a dimer and a standalone ITIC system. That was the right answer. I don't know if I get the question right.
I hope you did satisfy the curiosity. It was not an exam question. It was just curiosity about how system is composed. Amir, do you plan to try to create densely packed periodic system of those, or it is something too complicated?
You mean some force field models, Dr. Killian?
Use force field packing, and then use the resulting cell as an input for VASP calculations.
Yeah, it's not big deal for me. But for instance, these days, as some part of other projects, we are doing several force field calculation. But how big the system should be? Do you have any idea with that? For sure,
Very, very, very small. Like right now, you have approximately, I do not know exact numbers, but you have approximately a cube 3 by 3 by 3 nanometers. And in this cube, you have one donor and one acceptor and a lot of vacuum.
Yes.
Right? So vacuum takes like 80% of space at least. What if, like if I would be doing this myself, I would double the cell so that you have another donor and acceptor, and then compress it so that resulting cell will have 2 donors and 2 acceptors.
So when you are talking about compressing, you are talking about iso compressing, so hyperstatic compression on the system?
Yes, or one should keep the cell size along Y the same so that it doesn't damage periodic boundary conditions.
Yeah, exactly. That was my concern.
To compress along X and Z.
Yeah, it's not a big deal for me, especially recently we developed generalized amber force field for that polymer system to be utilized in lamps.
So if it is really cheap to run, you can try several models with like 2 donors and 2 acceptors, maybe 4 donors and 4 acceptors. But know that if I know your strength is unlimited in doing force field and lamps, you can do maybe hundreds of those, but they will be not acceptable by VASP. So really, really small, but with minimizing amount of vacuum. And it is fine if the side group entangle and backbone is smashed into each other, because it is typically what happens in reality.
Yeah, I get your point. So you want to replace those models with the current model, or just want to take a test to see how the results
just
look
try it as a test, and we'll discuss it again. As a backup plan, we will continue with the model that will be created and start with molecular dynamics. But maybe if new models will look promising, we can either add them to the plan or just change completely to the new models.
Okay. How many atoms is the maximum limit for us?
We shouldn't overcome 1,000. Well, if we do not do molecular dynamics, if we do just single point calculations, then VASP can take like 3,000 atoms. But so if we do
molecular dynamics,
but if we plan on molecular dynamics, it shouldn't exceed 1,000. And please check. I think Aaron was recently doing huge models. I remember it was around 1,000 atoms and around 3,000 electrons.
Okay.
Is it right, or there are more exact numbers?
No, that's about right.
Yeah, very good suggestion, Dr. Killian. It's not big deal for me. I can do that with our platform in force field molecular dynamics. And yeah, I will keep you posted, and we can discuss it later to how the results looks like, and then we can start some DFT calculation on them.
Okay, then please join me in thanking Amir. Very interesting new directions. And are there any additional questions to his presentation?
I guess I have one. So what exactly makes PCMB like a good acceptor? aside from it having like the right like homo-lumo energy offsets?
Uh, I'm not sure about that, Aaron, but it seems that for some synthesized purposes, it has a good solubility with chlorobenzene. So maybe it's easier to polymerize that or pack that with those conjugated polymers, especially with P3HT. But according to the literature that I read recently, yeah, charge mobility and solubility, they mentioned these two properties for the PCBM, and the most disadvantages was aggregation that this acceptor unit caused in the bulk system. So those two, I guess, ones of people in polymer community are going to maybe replace that by ITIC. But I'm not 100% sure. If I got something new, I will present them in the coming group meetings.
Okay, let me add.
For sure.
It's not my specialty. I can say something silly, but it was a big enthusiasm in the community about this full length buckyballs because it looks like artificial atom. It is composed only of carbons, but it is highly symmetric, and its electronic structure has it's like a quantum dot. So the energy levels are very much offset. On one hand, it is quite rigid, so it's a unique structure, unique organic structure with very well defined electronic properties. And just by coincidence, the offset between HOMO and LUMO is quite big, and the relative like Fermi energy or ionization places this electronic orbitals relatively low on the absolute scale. So it just matches the needed arrangement of levels. So it definitely Fullerene was not designed in a process of search of a best acceptor. It first was discovered as a just new form of matter that happens if one does laser ablation of the graphite, and later on it was found promising as a acceptor for plastic solar cells.
Mm-hmm. Yeah, I guess the reason I just ask is because like the LUMO orbital that was shown looks like it's just mostly contained on the ball.
Mm-hmm.
There's not a lot of chemical functionalities to it, so it's just kind of surprising that it shows good charge mobility, like between the like various other buckyballs in the blend. I guess the reason I ask is if you get to the point of doing dynamics on them, you could calculate like rates that the charges transfer between the donor and the acceptor units.
Mm-hmm. So buckyball without functionalization has only carbons, and so it doesn't have any mobile ligands. Doesn't have hydrogens. Doesn't have longer ligand groups as quantum dots have. So in some sense, it is naked. It's not isolated, and its orbitals are, although they are well characterized, but they are protruding in space. And if one brings together several of these fullerenes, then the overlap of orbitals from one fullerene and another will be noticeable. And if there are, it's not hypothetical, it is experimental way to form this artificial solid of placing this spherical structure in the BCC crystalline lattice when they prevent it from further compression by repulsion when they come really close to each other. And such super array of fullerenes allows hybridization between orbitals of one fullerene and another one. And this super solid also shows electronic structure and bands and mobility. So if they're not spaced by other components of the blend, then it is what Amir mentioned. They aggregate and form clusters of this. So they behave like atoms. If it makes sense.
Mm-hmm.
Yeah, interesting discussion. Any more questions to Amir? If no, let's thank Amir once again.
Thank you.